What's up guys, Major Math with another video on fluid mechanics. If you have any questions, drop it in the comments, and if you're having trouble with other problems, I've attached my email in the description, so please feel free to reach out. Without further ado, let's get started. Question 3.12 in the textbook says, as shown, a mouse can use the mechanical advantage, which is a formula that we'll be using, provided by a hydraulic machine to lift up an elephant. Part A says derive an algebraic equation that gives the mechanical advantage of the hydraulic machine below. Assume the pistons are frictionless and massless. And then part B says a mouse can have a mass of 25 grams and an elephant has a mass of 7,500 kilograms. Determine a value of diameter 1 and diameter 2 so that the mouse can support the elephant. And I actually think I cut out the part. It says to assume. We need to assume a value of diameter 1. We're going to go ahead and just write this in. Let's say that diameter 1 equals 100 millimeters. That should be enough diameter to fit a mouse. And that is equivalent to 0.1 meters. Okay, first step is always to figure out our goal, right? Write down our goal. So our goal is to find a value of diameter 2. Diameter 2 being the diameter for the elephant. So find diameter 2 that can allow the mouse to support the weight of the elephant, right? We're given that the mouse, which equals the mass 1 is 25 grams, so mass 1 is 25 grams, which we'll go ahead and convert that because we'll need it later, is 0.025 grams, kilograms. And then we're also given that the mass, I'll write it down, the elephant, I'm not going to put an equal sign, I don't like that, put an arrow, represented by mass 2 is equal to 7,500, I believe, yeah, 7,500 kilograms, okay? Yeah, we're already, I'm not going to write it down, we're assuming that the pistons are frictionless and massless, so we don't have to take that into account. Okay, so I underline this mechanical advantage because it says it in the problem and we're going to have to use that formula. We don't use this much in fluids. I think this is like the only time I ever have used it, but it's important, I guess. So mechanical advantage is found in the textbook. If you look up equation 3.6, you can find it. So the mechanical advantage, all it is measures the ratio of output force to input force in a system. So write that out in math terms. So mechanical advantage equals output force over input force, right? That's that ratio. So in this case, it's saying shown a mouse can have, so that it says right here, so that the mouse can support the elephant. So the input force is the mouse and the output force is the elephant, right? We're trying to find the diameter needed for that mouse to be able to hold up the elephant. Okay. Also gives us the equation in the textbook. I think it's, yeah, equation 3.6 again. Has a mechanical advantage equals force number 2 over force number 1. Just basically just what I have here. And then you can also do it with other ratios. So area 2 over area 1 equals diameter 2 squared over diameter 1 squared. So these ratios also work with area and diameter. The forces in this case, right, we only have this, the force of the piston acting up onto the mouse, and then we have the weight of the mouse acting down, right? Let's say our normal force, right? I don't know if you can see this. This has normal force of the weight of the mouse going down. Same with the elephant. Normal force up, force of the weight of the elephant going down. Okay, so we know we can go ahead. We're not interested in this, right? Because we're trying to find diameter, and we know we can use this for the force of the weight of the mouse and elephant. Sorry, output force of the elephant and weight, that's the only force being used. And then we have the input force of the mouse, which is just weight. And then, yeah, should be equivalent to the diameter of the piston for the elephant squared, and the diameter for the mouse squared. Right, okay. So we know that the weight equals mass times gravity. And then we know the mass of both of the mouse and the elephant, so we can just keep it in this form. We know we can actually solve for diameter. We're missing diameter 2, right? Yeah, so this is the diameter for the elephant. We're trying to solve for that. We have mass, we have gravity. We can plug that in, and we should be able to rearrange it and then solve for it. So we got M2, it's the elephant times gravity, and then we have M1, is gravity, equals diameter of the elephant squared, diameter of the mouse squared. These gravities will just cancel out, and you can rearrange this to solve for diameter 2 for the elephant. Right, and then we can get it all, square it, square this, and then we'll have right. Yeah. So we know this is the mass of the elephant. We know that. We know the mass of the mouse, and then we assumed a value, like the textbook said, of a diameter for the piston for the mouse, which we just assumed that to be 100 millimeters. So we can go ahead and plug all this in. This will equal 0.1 meters for the diameter of the piston for the mouse. Then the mass of the elephant is 7,500 kilograms, all over the mass of the mouse, which is 0.025 kilograms. And then if we put that in a calculator, we get the diameter of the piston for the elephant needed for the mouse to support the weight of the elephant is 54.8 meters. If you guys do this problem and assume a different value, you should be able to do the same process, but you will get a different number. Okay, so we know this formula. Force equals surface tension times length of the wetted perimeter, okay? And we also know that force of the weight is equal to mass times gravity, okay? So, and then we have this right here. We know that from what we know in statics, and this is in equilibrium, right? This is what it's going to look like with that, like at any moment in time when you have these two walls. So we know that the force of surface tension is going to equal the force in weight, right? So we gotta, I'll do this too. We know we can plug this in right here, and we can plug mg in right here, right? And before we do that, let's rearrange, because we gotta find, like, we don't know where we're gonna, how do we find height from this? How do we implement the variable height into these equations that we know we gotta use? So we gotta do some rearranging. So let's rearrange this weight one first, right? So let's look at mass. How do we rearrange this mass to get height involved, or this force of weight? So we know that density equals mass over volume. We can rearrange that to density times volume equals mass, right? So let's go, and then we'll just go ahead and rearrange the volume, right? So we know from the volume we can get the variable height from it. So let's rearrange it again and say that volume is equal to length times width and height, right? Because we're dealing with a rectangle here. So length times width times the change in height, right? So now you can see where we're getting this variable height from, and we can actually end up solving this. And this equals mass, okay? So let's plug this in for mass. So rearrange this to density times length times width times height times gravity. Okay, and then we need to rework this to make this represent the wetted perimeter. So when we're looking at this, what is going to be the wetted perimeter? So it's just two walls. There's nothing like in front. We're not taking a cross section and looking at this. It's literally just those two walls. So the perimeter is just going to be the length of the whatever, how deep this goes back. See what I'm saying? That's going to be the length. So this is just going to be, is just going to equal, the wetted perimeter is just going to be 2 of the lengths, right? Because it's just 2 walls. So let's go ahead, and this is the main equation we're looking at. Let's plug this in for there, and let's plug in this right there. Let's go ahead and do that. Density times length times width times height times gravity. We see that we have a length on both sides, so we can actually go ahead and cancel it out. So we end up not needing to know the length, which is useful. We know the width, right? It's separated by 1 millimeter apart. So we know that this is that 1 millimeter, or 0.001 meters. And then we know density from the textbook. It's up here, written right there. Oh, no we don't. Do we need density? We might need density. No, we don't need density. We could use density of this, but we can also do, we know that specific weight is density times gravity, so we can actually just rearrange this to look like, right, because specific weight equals density times gravity, so we can just replace this density and gravity with just specific weight. That's what I did in my notes, sorry about that. And then and we need to solve for the change in height. So let's rearrange this to solve for change in height. Right. I did that backwards, didn't I? Right, so I just divided by specific gravity, and the width, moved it over. Okay, so we're left with this formula, and we can go ahead and plug everything we know. So this will equal 2 newtons per meter over specific weight, 900. Width is 0.001 meters. Change in height, if you put that in the calculator, we'll get 0.015 meters. Multiplied by 1,000, it's 15 millimeters. So the max capillary rise will be 15 milliliters. Thanks for watching, soldiers. Don't forget to leave a like and subscribe for more content like this. If you have any questions, leave it in the comments, and if you need help with any other problems, feel free to contact me with the email shown on the screen.